Welcome to the course, Machine Learning with Hands-on Experience in Python and R, under Part 3C, such as Decision Tree Classification, Random Forest Classification, and Evaluating Classification Models Performance. This course is fun and exciting, but at the same time, we dive deep into machine learning. It is structured the following 10 parts to be the master machine learning on Python and R. In this video of Part 3C, we will discuss following 3 important parts of classification.
Hello and welcome back to the course on machine learning. Today we're talking about decision trees. Alright, let's get started. You might have heard the term CART. It stands for classification and regression trees. And this term is an umbrella term for 2 types of trees, which are obviously classification trees and regression trees. Now, the difference is that classification trees, they help you classify your data. So they work with categorical variables such as male or female, apple or orange, or different types of colors and variables of that sort. Whereas regression trees, they are designed to help you predict outcomes which can be real numbers. So, for instance, the salary of a person or the temperature that's going to be outside and things like that. So those are the 2 different types, and we're going to be talking about classification trees in this section of the course. So here we've got an example with lots of points on our 2-dimensional scatter plot. Now, how does a decision tree work? So what it's going to do is cut it up into slices in several iterations. So let's have a look. So there'll be split 1, there'll be split 2. So split 1 split our data at x2 equals 60, split 2 split our data at x1 equals 50, split 3 split our data at x1 equals 70, and split 4 split our data at x2, it's not shown here, but it's about 20. So that is how a decision tree works, and the basis for these splits. So how are these splits selected? How does the algorithm know where to select the splits? Well, basically, if you have a look at it now, then the split is done in such a way to maximize the number of a certain category in each of these splits. So to maximize, for instance, we want maximum red categories here, and here it's still the same, but then the next split maximizes the number of green here and the amount of red here. It's a very basic way to explain it. In reality, there's some complex mathematics happening in the background. The split is trying to minimize entropy, and so it's informational entropy. It's a very interesting term. It would take hours and hours and hours for us to go through all of that right now. And so if you want to get into the deeper mathematics behind this algorithm, then you certainly can research that. But for us, it's sufficient that we're just looking for the optimal split, or the algorithm is going to find optimal splits that are going to maximize the number of different points in each one of these new pockets, or they're actually called leaves. So you've got the starting scatter plot, and then at the end you've got these leaves, and the final leaves are actually called terminal leaves. So that's how the splits occur. And now let's rewind a bit and let's do that whole procedure again. But while we're performing the splits, we're going to start constructing a decision tree, an actual decision tree. Let's have a look. So there's our split number 1. And what it's doing is it's splitting our data at the 60 level. So now let's construct a decision tree that's going to ask exactly that question. So is x2 greater than 60 or less than 60? So if it's greater than 60, it falls into one branch. If it's less than 60, it'll fall into the next branch. So there we go. x2, is it less than 60 or no? Yes and no. Next is split 2, only splits the data that is above 60 in the x2 variable. So let's have a look at that. We're only dealing with data that is above x2, so it's over here. And now we're checking, so I'm going back now. Now we're checking as split 2 happens at 50 for the x1 variable. So here we go, x1 is less than 50, yes or no. So if, and here you can see that right away, this split already can tell us whether something is green or red. So if it's less, so if we're already above 60 and then below 50, then it's green, which we can see here. If we're above 50, then it's red, which we can see here. So that's how this classification works. And now let's deal with the remainder. So here we've got a split 3 happening at 70. If you're below 70, you're obviously going to be red. Otherwise, we're going to need to do another split. So below 70, then it's red. No, we got to do another split 4. If it's above 20, then it's green. If it's below 20, then it's red. If it's above 20, then it's green, so that's a no. If it's below, then it's a yes. So with these decision trees, a good way to structure them is to always keep yes, 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 yes on one side. So like if you're looking for yeses, they're always going to the left. Looking for no's going to the right, or vice versa, so just don't mix them up. And then the terminal leaves will predict exactly what color or what class is left. But at the same time, even if you don't get to the terminal leaf, because this is a very simple tree, trees can be very, very long, and so sometimes you might not even get to the bottom. So if you want to classify a new observation, and for example this observation falls into this section over here, then it would go down this road, then here, and then it would go here. But let's say you don't even get to the end, you get to somewhere over here, then in these boxes that still have a mix, so here you can see there's a mix of green and red, then the rule here is that a probabilistic classification occurs. So here we know instead of checking this last condition, we'll just check what is the likelihood of it being green and red. So here we see that there's more green than red. So if we're just going to leave it at this box, then we'll just say that it's a green dot. Whereas if we leave it at this whole box, if we just do this part, so we only check the first condition and then we leave it here, then we would automatically say that it's a red dot if we don't go down the decision tree and check more conditions. So that's another way of using the decision tree. Instead of going down to the very end, you can stop at any point and then just use the probabilities to predict your classification. And another thing is that it doesn't always have to be the two variables. So for instance, in a decision tree, just like with any other machine learning algorithm, you can have a multi-dimensional data set which has lots of different columns. So in our case, we only have two, but you might have lots and lots of columns, and then you could have a mix of questions being asked here, and that's up to the algorithm to come up with those questions. And as a final note, I wanted to mention a little bit about the history of decision trees. Decision trees have been around for a very, very long time. And in fact, they are so old that they have recently kind of started to die off. They were still popular about 20-30 years ago, but recently more sophisticated methods have come to replace them, and decision trees stopped being so popular. And that's continued for a while until recently they were reborn with new upgrades, so to speak. And those upgrades are additional methods that build on top of decision trees, and such methods are random forest, gradient boosting, and other methods. And in this part of the course, we'll look at least at one of those other methods. The point is that decision trees are, though a very simple tool, they aren't very powerful on their own, but they're used in other methods that leverage their simplicity and create some very powerful machine learning algorithms. And such algorithms even are used to perform facial recognition, like on your iPhone you have facial recognition, and also some games such as Kinect, which is kind of like the Wii, but you can play it without actually holding a control. So it's like a game for your addition to your Xbox, and you can play it without having a control in your hand, so it kind of recognizes where you're moving your arms and legs. And that method, Microsoft decided to use random forests for that method, and random forests invoke decision trees. So hopefully you enjoyed today's tutorial. It is quite a simple method, but at the same time it lies in the foundation of some of the more modern and more powerful methods in machine learning. I look forward to seeing you next time, and until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for this section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout this section as well. And you'll also need the machine learning template folder, which we're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, two words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right-click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. I'm super excited because today I'm going to show you a new kind of classifier with new kinds of prediction regions and new kinds of prediction boundary. You're going to see it's quite different from what you've been seeing so far, so I can't wait to show you the final graphic results. Let's go to File Explorer here to set our folder as working directory. So right now I'm going to part 3 classification and decision tree classification. Here we are. Make sure that the social network add CSV file is in the folder, and you can click on this button to set this folder as working directory. Alright, and now let's use our classification template. Let's take everything from here to the bottom, copy, and let's go back here and paste it here. Alright, let's change the titles of the graph here. Here our classifier is decision tree, as well as here decision tree. Alright, and now what we only need to do is to create our classifier here. By the way, decision trees, as you saw with Kirill, are not algorithms based on Euclidean distance. So we would not really need to apply feature scaling here, because feature scaling is, as I explained in the part 1 data preprocessing, is a must-do preprocessing step when your algorithm is based on Euclidean distance. But here, since that's not the case, we would not really need to do this. Besides, when we are making some decision trees model, we want some interpretation, because we can plot some trees to represent all the different conditions in a decision tree. And in the conditions, of course, you don't want to have your scaled value, you want to have the real original value, so you wouldn't apply feature scaling. However, when we plot those prediction regions here, we use a resolution of 0.01. That means that the code here to generate the plots will execute a lot faster if the variables are scaled. So that's a compromise here. We will leave the feature scaling here because we are plotting this plot with the high resolution. But know that if you want to plot some decision trees like the real tree itself, then you can remove this feature scaling part here to have the interpretation of your variables. So here let's keep it this way, and now let's build our classifier. So we're going to import the decision tree classifier class from sklearn.tree, and then we're going to create our classifier object of this class, and then we will fit this object to the training set as usual. So let's first import the class, so it's from sklearn.tree, and then import and then decision tree classifier. That's your class. That's the class we will use to create our object and fit it to the training set. And let's create the object, classifier equals decision tree classifier. And then let's inspect this class to see what arguments we need to input. So command I to inspect, and here we go. So parameters. The first parameter is criterion. Okay, so I know it says the default parameter for criterion here is Gini, but we will take the decision trees based on entropy. The most common decision trees are the ones based on entropy. You actually have a lot of amazing classifiers based on entropy, like maximum entropy for NLP. We will see that's in the NLP part. So we will get used to this entropy criterion for the information gain. And basically this entropy here is, as it says, a function that measures the quality of a split, so that at the final nodes of your tree, you want each node to be as much homogeneous as possible, that is, with users of the same class. And after each split, the more homogeneous is a group of users, the more the entropy is reduced from the parent node to the group child node. And so after the split, if the entropy in the resulting child node is 0, then that means that this child node is a fully homogeneous group of users, with only users of the same class. And the information gain mentioned here is basically the difference between the entropies before and after the split. So that means that after the split, the higher the information gain is, and the more homogeneous groups there will be after the split. So let's get used to this. Let's get used to this entropy criterion. And so here let's choose criterion equals entropy. Alright. Then the next parameters are not very important. So far we only want to focus on building the tree and making some quite good classification. We will see how we can improve the decision tree, and then we will play with those other parameters. But here we will only take the random state parameter just to have the same results, so you can follow the course with me more easily. The random state equals 0. Okay, and now we just need to fit this classifier to our training set. So we use the fit method here, and we apply it to xtrain and ytrain. Alright, and now the whole code is ready. So let's first select the section here that pre-processed the data. Here we go, all pre-processed correctly, perfect. Let's go to Variable Explorer. Everything looks good. Now let's create the classifier by executing this code section here. Alright, all good. You can see that all the parameters that we saw in the class are here the default parameters, because we didn't specify them. Now let's do some predictions. Let's apply the classifier to predict new observations, the test set observations. Here we go, ypred, and here's ypred. Let's quickly compare it to ytest, just to see how it looks. Okay, wow, this looks very good. As you can see, so far these are correct predictions. Let's look at 10 to 19. Okay, so from 1 to 9 that was perfect, but from 10 to 19 we see some incorrect predictions here. The 13th, the 15th, the 16th, and that's all. Okay, so, but now let's look at how many incorrect predictions we have on the confusion matrix. So let's execute this, and we are ready to find out. So let's take the confusion matrix here, and it looks pretty good. 9 incorrect predictions. Very good, that's an improvement compared to our other models. For example, in logistic regression, I think it was 11 incorrect predictions. And then we had much more incorrect predictions with the SVM. So here it's doing a pretty good job. Okay, and now let's get to the fun and exciting part about visualizing the result. And here it's even more exciting because we are going to get something different. If you followed the intuition course with Kirill, you might guess what kind of prediction boundaries we will get. Try to actually guess what's going to happen. It's a good exercise, good practice. This will allow you to combine your, intuition with practice. So you can pause on the video, you can think about it. Now I'm going to select this, and now showtime. Let's execute this, and here is the decision tree graphic results. Let's enlarge this. Alright, so quite new, right? This is very new. Remember, we either had some straight line when the classifier was linear, or we had some kind of a curve with a lot of irregularities when we used the KNN classifier. We also have some beautiful smooth curve with kernel, SVM and naive Bayes. But now we have something very different. First of all, the prediction boundary is composed of only horizontal lines and only vertical lines. That's exactly what you saw with Kirill in the intuition tutorial about the intuition of decision trees. You see that it's making some splits based on conditions on the independent variables, which are the age and the estimated salary. So we can clearly see here how, it's taking some conditions on some intervals of the variable age. So for example, here it's a condition where the estimated salary is between this value and this value, and the age is between this value and this value. So these are all conditions based on intervals of the independent variables. We can clearly see that here. So that's why the prediction boundary is only composed of horizontal lines and vertical lines. So yeah, that's something pretty new. So wow, so how can I describe this? Well, first of all, we are seeing that it's really trying to catch every single one of user in the right category. Here you can see it doesn't want to miss anyone. Even those red users who were clearly in the green region, like for example this one, well, there clearly was an effort here to catch this red user who is mostly in the green region. However, is there something that is striking your attention and telling you, be careful? Well, yes, we should be careful because this kind of looks like overfitting. Because you see it's trying to catch every single user into the right category. So I'm not sure that on some new observations, those regions here catch the users the same way with the same, correct predictions. So we'll see that right now on the test set. Let's close this. And let's select this to have a look at the test set. Execute, enlarge, and here is the test set. So actually that's not too bad. Here, for example, this red rectangle here that in the training set was catching some red points because there was red points in the training set. But we can clearly see that from some new observations, unfortunately here the new observations happen to be green. So that's too bad for this red rectangle that doesn't work for some new observations, especially these ones here. And it's the same, for example, for this rectangle that doesn't catch anything here because there is no new observation point of the test set, no new user of the test set in this red rectangle. So this is absolutely unuseful here. This was just to overfit the training set. So we have to be careful with this, but don't forget at the end of this part is a section about evaluating and improving the classification models. So hold on to that. And by the way, we can still say congrats to this decision tree classifier because it did actually a pretty good job. And by the way, we found 9 incorrect predictions. You can count them and you will count actually 9 red points in the green region plus green points in the red regions. Okay, so I'm curious now to see which classifier you prefer because we are approaching the end of our classification journey. We were actually introduced to a good deal of classifiers. We only have one left. It's the random forest. So you understand that here is one decision tree. So imagine if we do the same classification job with 500 decision trees. Imagine what the result will be. Try to already predict that in your head. You will understand with the intuition section that random forests are based on a majority vote of trees. So since this is one tree, imagine what a team, like an army of decision trees, will do to classify your points. I will let you find out about that. Okay, so that's the end of this tutorial. I was very happy to introduce you to the tree. This is actually a pretty cool model. I like this one very much. And don't forget that decision trees are very good for interpretation because you can build some trees to clearly see the conditions that are making the classification. We will actually plot this tree on R because you'll see that we can do this very quickly in one line and even with 2 words. So we'll do that on R, we won't do it in Python. Here I just wanted to show you the prediction regions, but we'll do it on R. And I can't wait to show you what an army of trees and random forests will do for you in terms of classification. Thank you for watching this tutorial. I look forward to seeing you in the next one. Until then, enjoy machine learning. Hello and welcome to this R tutorial. I'm super excited because today we're going to implement decision tree classification model in R. We just did it in Python for those of you who are here, and this excitement is due to the fact that we will discover a very new kind of classification. You will see that the prediction regions and prediction boundaries are something you haven't seen yet. So let's find out about that right now. So we'll quickly set our folder as working directory, part 3 classification, decision tree classification, and here is the folder. Make sure that you have the social network add CSV file. Then you click on this more button here to set the folder as working directory. Then let's quickly take our template, select everything from here to the bottom, copy, and paste it here. Alright, and now let's change a few things. So just not to forget, let's change the titles in the plot. So we will replace classifier by decision tree, and here as well. Okay, and now let's create our classifier. So in R, to create a decision tree classifier, we will use again the most popular library for that, which is the rpart library. So now just check to see if you have the rpart library in your packages. So for example, mine is right here. It might not be the case for you if you're starting R for the first time. So I'll just write this line of code for those of you who need to install it. And so as usual, it's install packages, and then in quotes in the parentheses you input the name of the package, which is then rpart. Alright, and then to install the package you need to select this line and execute. I won't do it right now because my package is already installed, so I'll just put that as comment. And however, we're going to include this line of code here, library, and in parentheses rpart, to automatically select this library, because once this is executed, this will be selected. As you can see right now, it's not selected, but it will be once this is executed. Okay, and now we are ready to create our classifier. So let's do this. Classifier, as usual, equals, and then we're going to use actually a function, which is the same as the library, rpart. So rpart, and in this function we will input the right parameters. So, well, as you can see right now, we can see what those parameters are, but if you want more info, we can click here and press F1, and here we just need to click here to get some info about rpart. Okay, so as we can see, the first argument is formula. So this is a parameter that we have to input, and as usual we're going to write the formula equals dependent variable tilde dot, and the dot is a shortcut to replace the sum of the independent variables, which is the other way of writing the formula. So that's the same as usual, and then we have the data argument here, which is of course the data on which you want to train your classifier. So this data will be the training set. Alright, so let's input the arguments. So remember, the first argument was formula equals purchased, that's the dependent variable, tilde, I just pressed Alt N, and then a dot to include all the independent variables. Then comma, and then we input the second argument, which remember it was data, and we pick our training set. Perfect, and now let's execute the whole code. So first we execute this pre-processing part here, as usual. Done, perfect. So we can have a look at the dataset all fine with our two independent variables, age and estimated salary, and our dependent variable purchased. Training set, all good, and test set, all good. Okay, so the training set and the test set are scaled because we will plot the prediction regions with a high resolution, so we need to scale. Actually, you can try to not scale the independent variables here, because for decision tree you don't need to scale your independent variables because the decision tree model is not based on Euclidean distance. But since we want to plot the prediction regions with a high resolution, you will see that your code will execute a huge time faster than if you don't scale it. Actually, I think that if you don't scale it, your code might break. You can try that, but be careful. So we will do it, but then we will execute the code again without the scaling to plot the tree. So we will clear everything, and in the pre-processing part, select everything except the feature scaling, and then we will plot our tree in a very simple way. But right now we want to plot the prediction regions, so we scale our independent variables. Okay, so perfect, now the classifier is ready, so let's execute it. Alright, all good. Now we can execute this line to predict the test set results. And actually what's funny is that ypred is not the same as what we were used to. First, for example, we can see ypred here. Remember before ypred wasn't in the data here, we had to type it in the console to have a look at it. And here it's here, so let's click on it to find out what it is. Alright, this is ypred, and this is actually a matrix of 2 columns and 100 lines. So what is this new ypred? What is it exactly? Well, as you can see, the sum of the 2 cells here in each line is equal to 1. So can you guess what it is? Well, these are probabilities. The first column gives the probability that the observation, the user belongs to class 0, that is, doesn't buy the SUV. And this probability in the second column is the probability that the user buys the SUV belongs to class 1, that is, buys the SUV. So here, if we look at the first observation, we can see that there is a very high probability that the user buys the SUV, 0.96, against a very low probability, well, of course, because the sum is equal to 1. And so that means here that the prediction here is that the user doesn't buy the SUV. And if we look at the test set here and look at the index 0, we can see that indeed, in reality, the user didn't buy the SUV, and therefore the prediction is correct. But that's because we have ypred this way in our template, and if you don't want this format of ypred, well, you just need to add a simple argument, which is type here. The type equals, and you just need to input class. Okay, let's try. Let's try to execute this line again, and here is ypred. Let's have a look at ypred now. Ypred. There you go. Now ypred is a vector, as you can see. For each observation of the test set, that is for each user of the test set, we have, like before, the prediction 0 or 1 for each user. 0 if the user is predicted not to buy the SUV, and 1 if the user is predicted to buy the SUV according to our decision tree classifier. Okay, so that's a little thing to change here. Make sure that you know your ypred is your dependent vector of results 0, 1 that we were used to, because here, as you can see, we use the same predict function with the 2 arguments classifier and new data equals grid set. So that means that this won't work because this is supposed to be a vector of prediction results, only this time it's for all the pixel points, you know, the imaginary pixel point users in the grid. But since the predict function is associated to the classifier, which is the decision tree classifier, and if we only keep those 2 arguments here, then this won't make any sense because this will return ygrid as a matrix of the 2 probabilities, and therefore here we will have some problem because it will be a matrix of a matrix, whereas here it's supposed to be a vector. So what we only need to do, and we will do it now so that we don't forget, is to add this type parameter, and we will set it equal to class, and then it will work perfectly. So we'll copy this and add it here as well. Perfect, and now it's ready. Now it will plot the graphs without any errors. So I know I gave you a template that is supposed to work without changing anything to plot the classifications. I'm sorry, sometimes we need to change a little few stuff, and that's why we need to, you know, execute each of the lines one by one to see if it's as it should be. And here, since we found out that due to this little different structure of the decision tree classifier, well, we need to adjust to get the right vector of predictions ypred that we had for the previous classifiers. And so we made the adjustment for decision trees by adding this type argument here and set it equal to class. Now we have the ypred vector that we needed. And besides, yes, we would have encountered some issues if we, you know, computed the confusion matrix this way with this ypred as a matrix of probabilities. But now it will be fine because ypred is set the correct way. So we'll execute this and look at the number of incorrect predictions. Alright, now let's enter CM here. And we have 6 plus 11 equals 17 incorrect predictions. So now let's see if we were right to change our code this way so that we can plot the graph. Let's see if it will work. I hope it will work because I want to show you the decision tree, prediction regions and prediction boundary. I really want to show you this for those of you who didn't follow the Python tutorial, of course. So let's select this and let's see if we made a good job. Alright, looks good. So far it looks good, no errors. Let's see what happens. And we were right. This works perfectly well. That's the decision tree classifier. That's the prediction boundary. So as you can see, there's only horizontal and vertical lines. That's because, as Kirill explained, the decision tree algorithm is based on some conditions of your independent variables by finding, each time intervals that will make conditions that will classify in some rectangles your observations. And actually what's funny is that we clearly have less overfitting than in Python, and actually that's why we have more incorrect predictions, because in Python we had, red rectangles here, red rectangles here. There was also red rectangle here. And here we didn't actually specify more parameters, but this amazing rpart library, and that's why it's very popular, chose the right parameters, the right default parameters to, prevent overfitting, because here we clearly don't have overfitting. We had overfitting with Python because of all the red rectangles here that were desperately trying to catch every user in the right category. But here it's not the case, and here it's doing a terrific job at, classifying correctly most of the red points here, most of the green points here in the right region, and as well as these green users here who couldn't be well classified for linear classifiers such as logistic regression or linear kernel SVM. So here it's doing a pretty good job, but still we have some incorrect predictions. That's because that's difficult to classify well if you want to prevent overfitting in your data. So even if we have 17 incorrect predictions, that's a very good classification we have here. Okay, but now let's look at the test set results, and I'm actually not too worried about that, because since we don't have overfitting here, then that means that we're very likely to have some good results as well on the test set. Let's check it out. Test set and execute. Let's see. And here is the test set. Okay, so as I told you, this looks very good. This is the set on which we have those 17 incorrect predictions. You can count them if you want, you will find 17. And it's classifying most of the red users in the red region and most of the green users in the green region, so that's quite okay. By the way, we can see that most of the incorrect predictions are here. We can see that we have many red points in the green region, so that's unlucky. But as I told you, we would rather prevent overfitting than trying to, minimize to zero the number of incorrect predictions. So there it is, another new kind of classifier, and therefore another new kind of prediction region and prediction boundary. And now in the next section you will find out about random forests, who are actually a team of decision trees, of many decision trees. A random forest can contain 500 trees, and so each decision tree of the team will vote for each data point whether this data point belongs to class 0 or class 1. That is, it will vote for each user if this user bought the SUV or didn't buy the SUV. And based on a majority vote, it will decide if each point belongs to the red region or the green region. And so I'm telling you this because, since here we have the job of one decision tree, imagine the job of an army of decision trees, like 500 decision trees. Imagine what it could do to classify the results. But let's not get too enthusiastic about that. Remember that we want to prevent overfitting, so let's find out anyway. Alright, and now time for the little extra bonus. Let's plot the decision tree. So in order to have the best interpretation, we're going to remove the feature scaling, and to do this we're going to clear everything and re-execute the code, but without feature scaling. So let's do this. We're going to clear the data here by clicking on this button here, and yes. Then clear the plots here, yes. And then clear the console as well by typing Ctrl L. Here we go. Alright, now everything is clear. We can re-execute the whole script. So let's do it step by step. We're first going to take all the pre-processing step, but without the feature scaling here. As you can see, I'm not selecting this. Alright, so now Command and Control plus Enter to execute. All good. And now you can see that if we go to our data set, training set, and test set, you can see that the features are no longer scaled. Alright, so for example, in the training set, we have the real age, with their real values, and the real estimated salaries, the real values. Okay, so nothing scaled now. Let's select this to fit the decision tree classifier to the training set. So Command and Control plus Enter to execute. Here we go, now it's fitted. By the way, I'm just going to replace this by decision tree classification. Alright. What we are really interested in right now is to plot the decision tree. So we're going to add a new section here below, and I'm going to call this section plotting the decision tree. And as I told you in the Python tutorial, this is going to take 2 lines. This is very simple, so let's just do it. It's going to be very quick. Okay, and besides, the 2 lines that we need to write could not be more simple, because indeed what we need to type here is plot, and then in parentheses, classifier. Because the classifier here is the classifier that we created here in this part using the rpart function of the rpart library, and that's all. We just need to type plot classifier, and that will plot the tree, but without the labels, without the conditions written explicitly. So in order to add these conditions written explicitly, we just need to add below text classifier. Here we go, and now it's ready. Isn't that simple? These only 2 lines will plot an interpretable decision tree. Let's check it out. I'm going to select all this and press Command and Control plus Enter to execute. And here is the tree. So as you can see, we have at each split the condition that is generating the split. So for example, the first split is made based upon the condition age lower than 44.5 years old. So that means that if the user is below 44.5 years old, he will go to this subcategory after the split. And if the user is older than 44.5 years old, he will end up in this subcategory of the split. And then we have some new conditions. So here, a new condition on the other independent variable, the estimated salary, and this condition is estimated salary below $90,000. So what that means is that if the user is younger than 44.5 years old and has an estimated salary below $90,000, then according to our decision tree classifier, this user won't buy the SUV because the result here is 0. And if the user is younger than 44.5 years old and has an estimated salary over $90,000, then according to our decision tree classifier, this user will buy the SUV because the result here is 1. Okay, and if we go to the other side of the tree, well, this other side of the tree first contains all the users that are older than 44.5 years old. And then we have some new conditions generating new splits. So another condition on the age here, then another condition on the estimated salary, and then again another condition on the estimated salary. And following yes or no these conditions, we end up in some final categories, the final nodes of the decision tree, where the user is predicted not to buy the SUV for this node, and predicted to buy the SUV for this node, and this node, and this node. Okay, so that was worth looking at this. We sort of explored this decision tree classifier behind the scenes, and what's important to understand now when you are using decision trees is that a big advantage of this classifier is that we can have these very interpretable results, because here on this decision tree plot we can see everything that's happening. We can see how the decision tree decides whether a user will be predicted to not buy the SUV or to buy the SUV. We clearly see the whole thinking process of the decision tree, and in some way we saw how it learned from the data how to classify each of our users of the social network. Alright, so I look forward to seeing you in the next section about random forest. We will implement random forest on Python and R, and I can't wait to show you the final graphic results. Until next time, enjoy machine learning!
Hello and welcome back to the course on machine learning. Today we're talking about random forests. Let's have a look inside. So first thing we're going to learn is a new concept, ensemble learning. What is ensemble learning? Ensemble learning is when you take multiple machine learning algorithms and put them together to create one bigger machine learning algorithm. So that machine learning algorithm, the final one, is actually using or leveraging many different other machine learning algorithms, and they can be the same machine learning algorithm as we'll see today. We're going to be looking at the random forest method, which combines lots of decision tree methods. So instead of running a decision tree method, which we talked about earlier, instead of running it once, we're going to run it multiple times, and that will give us a random forest. So let's have a look at the step-by-step process to understand how all of this happens. So step one is you pick at random k data points from the training set. Then you build a decision tree associated to those k data points. So instead of building a decision tree based on everything you have in your dataset, you build a decision tree just based on some of the data points that you have. So kind of like a subset of all of your dataset. Next, you choose the number of trees you want to build, and you repeat steps 1 and 2. And then once you have all of those trees and you have a new data point, so when you want to check where a new data point falls and how it's classified, for a new data point you make each one of your entry trees predict the category of which the data point belongs to, and then you assign the new data point to the category that wins the majority vote. So that's how a random forest works. So basically you start off with one tree and then you build another tree, another tree, another tree, and each one of those trees is being built on a randomly selected subset from your data. And even though each one of those trees might not be ideal, overall on average they can perform very well. And that's a major advantage of this algorithm. It's kind of leveraging the power of the crowd, so to speak. Instead of just relying on one tree, it's checking what all the trees are going to say and then just taking the majority vote and deciding the classification based on that. And that power of numbers can help get rid of certain errors and certain uncertainties in your algorithm and make it more precise. And in fact, it's such a good solution that when Microsoft were developing Kinect, you know, this device that allows you to play games on your television, that little device over there, it attaches to an Xbox, and then you can play games without any controller. So here, that device is using an infrared grid to understand where the hands, arms, head, and other parts of the body of these people are located and how they're moving. And it's using machine learning to understand how the body parts are moving and where exactly they're located in space. So when Microsoft was developing Kinect, they decided to go with the random forest algorithm over all of the other machine learning algorithms that were available to them, and use the random forest to develop this sophisticated piece of hardware/software. And actually they have a interesting article about it, so I'm just going to show it to you now. If you can find it on the internet, so it's at microsoft.com. This is from there, and you can definitely find it there. It's called Real-Time Human Pose Recognition Parts from Single Depth Images, and here it explains exactly, so you can actually see the random forest in action. So you can see that this is similar to what we were talking about before in the classification trees, but here it's actually using random forest to understand where body parts are, and then based on that the device finds what it needs to do in the computer game. So that's how it works. And so here, if I just search for the word forest, you'll see that decision forest, and they actually explain that they were able to achieve faster speeds, faster processing with the decision forest, and therefore that, you know, reduced the cost of the hardware that they required for this tool. Interesting article. Check it out if you want to learn a bit more about a real-life practical application of a decision forest or a random forest. And that's it for today's tutorial. I hope you enjoyed learning a bit about an ensemble type of machine learning algorithm. Definitely the practical side is going to be quite interesting as well. And I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for this section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout the section as well. And you'll also need the machine learning template folder, which we're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right-click extract here. If you get this macOS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the macOS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. We are finally getting to the final round of our classification adventure in our machine learning journey, because today we're going to build our very last classifier, which is the random forest classifier. So you're going to see that it quite looks like decision trees, because actually random forest is like an army of decision trees, each one predicting a result, and then based on a majority vote, the ultimate prediction is made. So if you understood correctly decision trees, you will have no problem understanding random forest and predicting the graphic results that you're about to discover in this tutorial. So let's do it. Let's start making this random forest classifier, and at the same time let's try to guess what we will obtain. Okay, so let's start by setting the right folder as working directory. So I'm going to File Explorer here, then Machine Learning AZ folder, Part 3 classification, random forest classification. As you can see, this is the last classifier that we build here, because then the next section is dedicated to evaluating classification models' performance and improving them. So yes, we definitely reached the final round. So let's do this. Let's go to our folder, make sure we have the social network add CSV file, and if that's the case, let's click on this button to set this folder as working directory. And now let's start. Of course, we're going to use our classification template, which is here. We're going to select everything from the top to the bottom, copy, and then paste it here. Alright, now let's make the basic changes, like here we are fitting random forest classification to the training set. Then here we will create a random forest classifier. Then let's change the titles of the plots here so that we don't forget later. So here we'll replace classifier by random forest classification. Because you know we're making the distinction between random forest regression and random forest classification, as for decision trees actually. Alright, so now we made the basic changes, and now let's make the main and most important change, which is to create the classifier here. So let's do this. It's actually really simple. As usual, we're going to import the right class for this job, which is the random forest classifier. As usual, it's very intuitive. Then we will create a classifier object of this class, which will be the random forest classifier itself. And then we will fit this random forest classifier to our training set that we created here. As a quick reminder, this section is the data preprocessing step. Here we import the libraries, the essential libraries. Here we import the data set. Here we split the data set into the training set composed of xtrain and ytrain, and the test set composed of xtest and ytest. And here we do some feature scaling, which is important here because since here we are plotting our graphic results with a resolution of 0.01, and that our classifier is going to predict the class of all the pixel points of our graph with a resolution of 0.01, we need to apply feature scaling here so that our code executes much faster. Okay, so that was a quick reminder, and now let's create our classifier. So as I just told, we are going to import the random forest classifier class from the sklearn ensemble library. So then we have to type from sklearn.ensemble, here it is, import, and that's where we import the class. And the class name is spelled this way, capital R, random, capital F for forest, and capital C for classifier. And here is our class. And now let's create an object of this class, which will be the random forest classifier itself. So let's do this. As usual, we call it classifier equals. Then we are going to call the class to create this object. So actually, let's copy that here. It will be quicker. Copy, paste, and here is our class. And now let's make some parentheses because we will need to input some parameters. And here let's inspect this class to see what parameters we have to input. So to inspect the class, we type command I, and here are the info about our random forest classifier. So let's look at the parameters, which is what we are interested in. Okay, so the first parameter is n estimators. That's actually the number of trees in the forest. So that's actually the number of trees which will predict if each user of the social network buys or doesn't buy the SUV. So okay, let's say we choose 10. You will have 10 trees predicting if each user buys or doesn't buy the SUV, and then based on a majority vote, the random forest will vote for the ultimate prediction, that is the prediction of the random forest, whether the user buys yes or no the SUV. So let's pick the default number of trees. You can actually play around and try some different numbers of trees, but here let's pick the default number of trees, which is 10 trees. So let's input here n estimators, and let's pick 10. So I strongly encourage you to play around and try different numbers of classifiers because you'll see you'll get different results. And if you do this, make sure to pay attention to detect overfitting. You know, remember, overfitting is simply when you fit too much your classifier onto your training set in such a way that when you want to predict new observations from a new set, like the test set, then your classifier will be kind of lost because it is used too much to the training set because it was fitted too much to it. So that's why it's very interesting for you to play around with the number of trees, because you can learn how to detect overfitting. Okay, and then what is the next parameter? The next parameter is criterion. So remember, in the decision tree section we chose the entropy criterion, which I remind is a criterion that measures the quality of your split in such a way that after the split, the more homogeneous are your new groups of users, the more the entropy will be reduced. Because you know, entropy is a notion in physics that represents in some way the disorder. So the higher the entropy is, the more your particles are in disorder. Well, here that's the same. The particles are the users, and the more homogeneous a node is compared to the parent node, the lower the entropy is compared to the entropy of the parent node. And the information gain is how much you manage to reduce the entropy from before to after the split, because it's the difference between the entropy of the parent node minus the entropy of the child nodes. And so as well as for decision trees, we will choose an entropy criterion here so that all our trees in the forest make their predictions whether each user buys yes or no the SUV according to the entropy criterion. Okay, so here let's choose criterion equals entropy. Alright, and now what is the next argument? Max features. Okay, this one is not really important here. We don't need it to build our random forest. We can use it later to improve and play around with our model. Same for these other parameters here. That's all about adding some variance in your model. But what we will add as usual is the random state parameter here and set it to 0 so that we all get the same results. So let's input it here, random state equals 0. And perfect, that's all we need to create our random forest classifier. So now that it is ready, let's fit it to the training set. So as usual, we're gonna take our random forest classifier here, and then we will use one of its method, well, one of the methods of the random forest classifier class, which is the fit method, of course, to fit this classifier to the training set. And here, in this method fit, we input the training set, which is composed of xtrain and ytrain. With this line of code here, our random forest classifier will learn on the training set how to make some future predictions, which will be actually our next code section. Okay, so let's now start to execute the code, and we are very close to find out about the results. I can't wait to show you, so let's do it right now. Let's start by executing the data preprocessing phase. So I'm going to select everything from here to the top. Alright, here I don't have anything to do. Everything is already made correctly thanks to the template. So let's execute this. Here, as you can see, executed properly. If we go to Variable Explorer, we can make sure everything is fine. We have our data set, our training set composed of xtrain and ytrain, on which our random forest classifier will learn the correlations and then learn how to make the future predictions. And then we have our test set composed of xtest and ytest, which will be the set where our random forest classifier will make these new predictions. Okay, so everything seems fine. Now let's execute this code section here to build the random forest classifier. Command and Control plus Enter to execute. Alright, perfect. Here we can see that we have all the default parameters selected by default. And here we have the confirmation that we have 10 trees in our random forest. So awesome. For each user of the social network, we will have 10 trees voting whether the user buys yes or no the SUV. So the result is promising. And so let's check it out right now. Let's make the future predictions. So here I'm selecting this to predict if each user of the test set will buy yes or no the SUV. So let's press Command and Control plus Enter to execute. And now we have our vector of predictions. So now what we're going to do is to compare this vector of predictions ypred, that is the real results whether the user buys yes or no the SUV, which are contained in the ytest vector. So here let's compare the truth and the predictions. Alright, so as a quick reminder, this is the truth. These are the true results that happen in real life. That is, in reality, did the user buy yes or no the SUV? And here are the predictions. That is, did our random forest classifier predict if yes or no each user bought the SUV? Okay, so far it looks quite good. We can see that for the 10 first observations, we have just one incorrect prediction, which is the 9th one. All the rest is correct, so that's not too bad. Let's look at the last 10 observations. Here we are. And again, when we look at the last 10 observations, we can see that we have only one incorrect prediction, which is on the 95th user, because in reality this user bought the SUV, because here we have a 1 in the ytest vector, which is the vector of true results, and in the ypred vector we have 0, which means that our random forest classifier predicted that this user wouldn't buy the SUV, and therefore the prediction is incorrect. Okay, so that was just a first quick look at the predictions, but now what's very interesting to see is the confusion matrix, because we will simply get the number of incorrect predictions. So let's do this. Let's execute this section. Command and Control plus Enter to execute. And here is our confusion matrix. Let's double click on it. And yes, that's what I was telling you. We have only 3 plus 5 equals 8 incorrect predictions. So that's a very good job, but be careful. We want to prevent overfitting. So we're gonna wait and see what happens with the graphic results. And we're gonna feel and detect if there is some overfitting. So let's press OK, and let's actually find out about that right now. So I'm going to select this section here and press Command and Control plus Enter to execute, and we will obtain the training set results. Here they are. Wow. Okay, so clearly there might be some overfitting here. Let's enlarge this. Okay, so quick reminder, the points here are the true results. That is, each point corresponds to each user of the social network, well, the users that are in our dataset, and the regions here are the predictions. That is, the red region contains all the users for which our random forest classifier predicts that the user doesn't buy the SUV, and the green region contains all the users for which our classifier predicts the user buys the SUV. Okay, so in short, the points are the truth and the regions are the predictions. And the prediction boundary is this limit between the red region and the green region. And as we can see here, we have a very different prediction boundary than what we had with the previous classifiers, and is close to the decision tree classification results. And that's because what's happening here, so right now we're going to explain what happened behind the scenes, is that for each user here, what happened is that there were 10 trees, because we chose to have 10 trees in our forest. There were 10 trees that predicted if the user buys yes or no the SUV. So that's like in the previous section. In the previous section we had one tree predicting that, and now we have 10 trees predicting that for each user. And then each of the 10 trees makes the prediction, yes or no the user buys the SUV, and then there is a vote, a majority vote. So the random forest counts the number of trees that voted yes, the user buys the SUV, and counts the number of trees that voted no, the user doesn't buy the SUV, and then takes the prediction that was voted the most times. So for example, this point here is in the green region. That is that among the 10 trees, there were more trees that voted yes, this user buys the SUV, than trees that voted no, this user doesn't buy the SUV. The random forest voted yes, because it's the majority vote, and therefore made the ultimate prediction to predict that this user buys the SUV. So that's what happened behind the scenes, and that's what I was telling you. If you understand how a decision tree works, then you understand how random forests work. It's actually quite simple. And therefore we obtain all these results. So as you can see, most of the red users are obviously well classified here. Most of the green users are classified here. Even the single points here that were in the green region could be classified correctly by this team of trees, because as you can see here, this red point, that is this user who didn't buy the SUV, is clearly in the green region here, and the random forest classifier managed to catch it and make a red region here containing some other red points, that is some users who didn't buy the SUV. But since this is the training set, we actually have very few incorrect predictions. And now what's interesting to see is if this overfitting result that we detect here will compromise the test set result. So let's check it out right now. Let's close this and let's select the last section here, which are the test set results, and press Command or Control plus Enter to execute and enlarge the graph. Alright, and these are the test set results. Okay, so first of all, we can clearly see that there were some overfitting. Why is that? Because for example, when we look at this red region here, remember this red region was made so that it could catch some red users in the training set, because our model learned how to classify the users that didn't buy the SUV and bought the SUV on the training set. And so there was this red region generated here to catch these users who didn't buy the SUV. But here, unfortunately, in the test set, this region contains some users who bought the SUV, because here we can see that we have this green point here. And same for this one, but our random forest classifier was lucky on this one, because this is green points, and it almost got into the red region. So that was almost an incorrect prediction. So our random forest classifier was lucky on this one, but that's the idea of overfitting. It made this red region here to catch the users in the training set because it learned how to classify on the training set. But unfortunately, when we have some new observations, this red region doesn't make sense at all and shouldn't be here. So the conclusion of all this is that the best classifiers that we had are maybe the kernel SVM classifier or even the naive Bayes classifier, because for these classifiers we had a smooth curved prediction boundary that, we're catching most of the red users here that didn't buy the SUV and put them in the red region, and at the same time caught well the other users that bought the SUV and put them in the right green region. And we didn't have these red regions here that overfit the training set and then caught well the users in the training set, but then don't make a good job at predicting new users in the test set because there are unfortunately not red users in this red region here. So yeah, that's the conclusion of all this, and that's where we can start thinking how to choose the best classifier for our problem. And it's always related to this battle between accuracy, having the maximum number of correct predictions, and preventing overfitting. So here clearly we want to prevent overfitting. We don't want to have this result here that don't make any sense here for new observations. So the conclusion of all this is that if we had to choose one classifier among all the classifiers that we saw for this specific problem, I'm not saying that this is the classifier we should choose at all times, it is the classifier we should choose in our business problem, in our situation here, is the kernel SVM classifier. Because we had some accuracy with a good number of incorrect predictions that was quite low, but at the same time was catching the red users in the red region properly and the green users in the green region properly without having these irregular regions here that don't make any sense for new observations. And of course, the kernel SVM classifier was better than linear classifiers like the logistic regression classifier or the SVM classifier, because remember we had some users here that couldn't be caught properly by linear classifiers because they were green users, that is users who bought the SUV, and they ended up in the red region, that is the region where the classifier predicts that the users don't buy the SUV. And with the kernel SVM, these green users here who bought the SUV were predicted correctly in the green region, thanks to this curve here that could encompass the red users in the red region without including the green users in the red region. So now I really have to say congratulations, because you built a great deal of classifiers. You built some very powerful classifiers that will be able to make some powerful predictions for your business problems. So right now you're loaded with a great deal of classifiers, and you now have some powerful tools in your scientific and technical luggage. So congratulations, thank you very much for watching these tutorials about classification. I will now do the same on R for those of you who are also interested, and then afterwards there will be a bonus section dedicated to how you can evaluate the performance of your different classifiers and therefore how you can improve your model performance. So I look forward to seeing you either in the next tutorial about random forest classification in R, or in the next section dedicated to evaluating and improving models performance. So I'll see you soon, and until then, enjoy machine learning. Hello and welcome to this R tutorial. We are finally getting to the final round of our classification adventure in our machine learning journey, because today we're making the very last classifier, the random forest classifier. So this classifier is basically the daddy of the previous classifier, the decision tree classifier, because very simply, a random forest classifier is a team of decision trees. So you will see that we will pick a number of trees to compose a random forest, and then when it is time to make a prediction, then each of the trees of the random forest will each one make a prediction, whether or not they think that the user would buy yes or no the SUV, and then the random forest will look at each of the votes of its trees, and then will count the number of votes for each class, that is the number of votes for yes, the user bought the SUV, and the number of votes for no, the user didn't buy the SUV, and simply based on a majority vote, the random forest classifier will choose the class that received the majority vote, that is the most votes from its trees, to make it as its ultimate prediction. So that's the idea about random forest, and therefore if you understood correctly decision trees, then you would have no problem to understand random forest. Okay, so let's make our very last classifier right now, and let's find out about the results. So let's start with the basics. We'll go to our machine learning AZ folder to set the right folder as working directory. So this right folder is in part 3 classification, and here it is, section 20, random forest classification. That's the right folder. And as I was telling you, we are reaching the end of part 3 classification, because the next section will be dedicated to evaluating classification models' performance in order to improve the models, and therefore this is our last classifier. So let's go to this folder. That's the folder we want to set as working directory. Make sure that you have the social network add CSV file, and if that's the case, click on this more button here and then set as working directory. All good here, and now let's go to our classification template to build our random forest classifier with the best efficiency. So we'll just take everything from here to the bottom, copy, and then we'll paste it here. Alright, so I'll just give a quick reminder about what this template is doing. So the first step is to import a dataset. We are importing the social network add CSV file that contains some data about users of a social network and their information like their age and their estimated salary. So this car company has just launched its brand new SUV at a ridiculous price, put ads on the social network, and the last column of this social network add CSV file tells if yes or no some users of the social network bought the SUV. So 0 if no and 1 if yes. Then we encode here the target feature as factor because we sometimes need to do it for the classifiers that we build. We're just doing this to specify to the classifier that our last column purchased is a categorical variable with factor levels 0 and 1. So we don't need to do it for all the classifiers, but we do need to do it for some, like the naive-based classifier as we saw. So it's good to keep this code section in the template. Then we split the datasets into the training set and the test set. So as a reminder, the training set is where our machine learning model, that is our random forest classification model, will learn the correlations between the age and the estimated salary and the question whether the user will buy yes or no the SUV. And then based on these informations, the machine learning model learns how to make some future predictions. And so we build this test set here to test the performance of our model in terms of predictions. And then in the last section of the pre-processing phase, we apply feature scaling to the data, and we are only doing this because at the end of this template we make this very cool graph for both the training set result and the test set results that will plot the prediction regions and the prediction boundary. Okay, so right now we need to change a few things in this template, but some very few things. First, let's not forget to change the title of the plot. It will replace classifier by random forest classification. We'll copy this because we'll do the same in the test set results. Here it is, perfect. Okay, and now what we only need to do is to create our classifier here, and then we'll be ready. So I'll just paste the same thing here, random forest classification to the training set, and now let's create our classifier. Alright, let's do this. So it's very simple. We're going to use a library that is called random forest. So let's do this. Let's first install the package with the command install.packages. So that's for those of you who are using this package for the first time, then you won't have it installed on your packages list here. As you can see, mine should be already here because I used it several times. Yes, there it is, random forest. So if it's not the case for you, then you need to install the package here. And so in this install.packages function, you just need to input the name of the library in quotes. So it's random forest. Be careful with the capital F here and not capital R here. Alright, so that's what you need to input anyway. That will install the package. I won't do it because I already have mine installed, but what you just need to do is to select this and press Command and Control plus Enter to execute. And this will install the package without any issues. Alright, so here I'll just press Command plus Shift plus C to make it as a comment. But then what I need to do is to add the command here, library, and then input the name of the random forest library, because as you can see here it's not selected, so I need to add this library random forest command to select it automatically, especially if I want to make some automated R scripts in the future. So that's a thing to do, that's very practical. And now we're all good, let's create our classifier. Okay, so as usual we'll start by creating the variable classifier. That will be our random forest classifier itself. And now we will use the random forest function to build our classifier. So here I'll just take the function random forest. And now let's see what arguments we need to input. So we'll just go here and press F1 to get some info about this function. So here we need to click here. And here are some info about the random forest library and function. So let's look at the arguments, which are what we're interested in. Okay, so the first argument is data. We won't need it, as you can see, it's an optional data frame. So it's not an argument that we need to build our random forest classifier. Same for subset and na.action. We actually don't need the 3 first parameters to build a random forest classifier. However, we of course need the x and y arguments here, which, as you can guess, will be the matrix of features and the dependent variable vector. Indeed, as you can see, X is a data frame or a matrix of predictors, so that's pretty clear. X is our matrix of features, our matrix of predictors, which are our independent variables, age and estimated salary. And then Y is set to be a response vector. So of course Y is the dependent variable vector that is the purchased column. Okay, perfect. And then the last argument that we will need to build our random forest classifier is of course the number of trees we want to have in the forest. And this number of trees is given by this entry argument here, which as you can see is the number of trees to grow. So to grow is a nice way of telling that the trees will learn from the dataset how to make the predictions, and basically this argument is the number of trees. So remember in the Python tutorial we chose 10 trees? Well, let's do the same here. Let's pick entry equals 10. And that is actually everything we need to build our random forest classifier. Only x, the matrix of features, the matrix of independent variables, y, the response vector, the dependent variable vector, and entry, the number of trees. Okay, so let's do this. Let's input the arguments. Let's go back to R, and here we are. Okay, so let's input the arguments. As you remember, the first argument was the matrix of features, the matrix of independent variables, and that is training set, excluding the last column, which has index 3. Because as you remember, in the training set we have the first two columns, which are the independent variables, age and estimated salary, with therefore indexes 1 and 2. And we have the third column indexed by 3, which is our dependent variable vector purchased. So here -3. Then what was the next argument? The next argument was y, the dependent variable vector. And then here we'll take training set, and let's pick it this way to specify the name of the independent variable. So $ here, and purchased. Purchased is the name of our dependent variable column. Alright, so we almost have everything we need. The last thing we need now is of course the number of trees, and that is entry equals 10. You can play around with the entry argument. You can choose many more trees in the forest. You'll observe some interesting results. That's interesting to see what different teams of trees can do to predict the response of your users in the social network, whether they buy yes or no the SUV. But if you do this, make sure to pay attention to overfitting, which you want to avoid. You don't want to overfit the random forest classifier to the training set, because if you do this, then it might make some poor predictions on the new set. You can actually check it out with the test set. But here we'll choose 10 trees and we'll see what happens. Alright, so actually we're done with the template. We changed everything we had to change, and now we can just, select everything and execute to make everything ready. We can actually take some coffee or tea, and you can just select everything and execute to watch the results. But let's rather do it step by step. We'll just do the first pre-processing step all in once here. So I just selected the pre-processing phase, and now I'll press Command and Control plus Enter to execute. Alright, all good. We have our data set, our training set, and our test set. So everything looks fine. We have 400 observations in total, 300 observations that went into the training set, and 100 observations that went into the test set. As you can see, the training set and the test set are scaled, because in the end we're plotting some graphic results with a resolution of 0.01. So in order for our code to execute faster and not actually break our code, we need to apply feature scaling to our training set and our test set. Otherwise we wouldn't need to do that, because the random forest classification is not based on Euclidean distances, but it's based on, conditions on the independent variables. But because of this code here that is compute intensive, we need to apply feature scaling so that everything is well executed. Alright, so let's do this. Let's watch the results. We just need to create our classifier here by executing this section. So here I'll just do this. Alright. Okay, now let's predict the test set results. Then we have the confusion matrix, which will tell us in a flashlight how many incorrect predictions we have. So let's actually do it directly. It will be faster to see how our random forest classifier did well on the predictions. So let's execute this. And now let's enter CM here in the console, press enter, and here we have our confusion matrix. Okay, we have 7 plus 10 equals 17 incorrect predictions. Well, that's not too bad. Just for fun, let's just pick another number of trees. Like, for example, let's pick 500 trees. 500 trees is a lot. That's really a big army of trees to make some predictions. And now, just for fun, let's take this. I don't need to include this because my library was already selected from the previous execution of this code section here. So let's rebuild a new classifier with 500 trees, and now let's look at the confusion matrix. But before, let's build our vector of predictions, because right now the ypred vector of prediction is the one given by the random forest with 10 trees. So let's re-execute this. All right, now we have ypred as the vector of predictions predicted by the random forest with 500 trees. And now let's look at the matrix of predictions. Remember, with 10 trees we had 17 incorrect predictions. And now let's see, select, execute, CM, enter, and now we have 15 incorrect predictions. Great, we invested 490 more trees to win 2 correct predictions. So definitely that means that there are a lot of unuseful trees in the team. Okay, so as you want, let's maybe go back to 10 trees here, because obviously 500 trees is not very useful. All right, so I'll just take that again, that as well, and that as well. All right, and now let's look at the training set results. So everything is fine here. We changed the title here with random forest classification, so it's all good. We are ready to look at the graphic result. And by the way, you can pause on the video now and try to guess what you're about to see. Try to guess the shape of the prediction regions and of the prediction boundary. If you understood correctly the decision trees, then you would have no problem guessing what's about to happen. Alright, so I'm going to execute right now, Command and Control plus Enter to execute, and showtime. Alright, wow, that's quite something here. Okay, so first I'll give a very short and quick reminder of what this is about. So the points here are the real observation points, that is the real users of the social network. The red points are the users who didn't buy the SUV, and the green points are the users who bought the SUV. And then we have the regions here, the red region and the green region, which are the prediction regions. So the red region is the region where our random forest classifier predicts that the user doesn't buy the SUV, and the green region where a random forest classifier predicts that the user buys the SUV. Okay, so in short, the points are the truth and the regions are the predictions. And now let's see, okay, so the random forest classifier definitely catches most of the users that didn't buy the SUV in the right category, that is the red region, so that means that it classified well most of the users who didn't buy the SUV. And same for the green users, who are the users that bought the SUV in reality, because as we can see, most of them are in the right green region. And it's desperately trying to catch some outliers, we can call them this way. For example, this guy here is a user that didn't buy the SUV in reality because this is a red point, and it is way into the green region here, as we can see, but the random forest classifier managed to make this little rectangle part of the region in red to catch this user that didn't buy the SUV and classify it well. But is it the smart way of doing this? Because what will tell you that for some new observations we will have, some users who didn't buy the SUV in this red rectangle here. So that looks like overfitting, because it made this red rectangle here because we had this user indeed who didn't buy the SUV, but nothing tells us that for some new observations we will have some users who didn't buy the SUV in this red rectangle here. So we should be careful with that. And same for this user here. As you can see that this user is in some sort of a irregular red region here. But fortunately, our random forest classifier was not too obsessed at making all predictions correct, because as we can see, this red user here is in the green region. So that means that it still paid attention to overfitting, but not too much, and we should be careful with that. So speaking of overfitting, let's check that right now. Let's look at the test set results right now to see how this regions here, because the regions won't change. These are the regions built by our model. So when we look at the test set results, we will have the same red region here with this rectangle here and green region here. But what will change will be the test set observation points, that is all the red points and the green points. This will change, and we will see if we have some red points here in this rectangle here, and actually probably not, because this looks like overfitting that occurred because our classifier was fitted too much to the training set. So let's find out about that right now. Let's select this section dedicated to visualize the test set results. So I'll just select everything and press Command and Control plus Enter to execute. Alright, so what is the first thing you see here? Well, yes indeed, this red rectangle here is totally unuseful for some new observations. So that was clearly a red rectangle region to catch some users of the training set, because our classifier was too much fitted to the training set. And this red rectangle actually doesn't make any sense here, because indeed we don't have any red user in this rectangle region here. Well, it's not that it doesn't make any sense, but it's totally unuseful here. And besides, you know, we have this green point here, and this green point could have been in this region here that would make an incorrect prediction. We were lucky on this one, but this could have happened because these are new observations, and our random forest classification machine learning model didn't learn anything from this new observation point. So this guy could totally have ended up here. So lucky on this one. And by the way, same for this region here, we don't have any red user, that is some user who didn't buy the SUV in this red region, so this red region is totally unuseful as well. Okay, so that's the idea, but most of all, it did a pretty good job, because of course it caught most of the red users here with a low age and a low estimated salary, and therefore users who didn't buy the SUV, and most of the green users who are quite older with a higher estimated salary, who bought this awesome cheap luxury SUV. Okay, and now what is the conclusion of all this? Because we reached the end of our classification adventure. We built all our classifiers, so according to you, what is the best classifier for this particular business problem? What is the best one? It should be a classifier that classified correctly the users who didn't buy the SUV and the users who bought the SUV, and at the same time prevented overfitting in the training set to be able to make some good new predictions of some new observations. So, in my opinion, the best classifier would be the kernel SVM in terms of the balance between the percentage of incorrect predictions and the fact that we want to prevent overfitting. Well, if we look at them again, in my opinion, the kernel SVM classifier would be the best one. Alright, so that's the end of this tutorial, and now I have to say congratulations, because you built a great deal of classifiers, from simple classifiers with logistic regression to more sophisticated and more complex classifiers like kernel SVM or random forest classifiers. But that's not the end of the journey. In the next section we will be talking about how to evaluate the performance of our models and how we can improve them. And then eventually we will have a homework on a real-life data set where we will combine what we learned here about how to build some classifiers and all the next concepts that we will learn to evaluate the model performance in order to find the best model for this real-life business problem data set that you will be given, and we will do the job as a data scientist or a machine learning scientist would do in reality. So congratulations again, I look forward to seeing you in the next section, and until then, enjoy machine learning!
In this tutorial, we will be talking about false positives and false negatives. As you remember, where we were using the logistic regression function to observe where 4 random values of the independent variable will end up in terms of y hat, so in terms of the predicted value for the dependent variable. And we agreed that anything below the 50% line will be projected downwards onto the 0 horizontal line, and anything above the 50% line will be projected upwards onto the 100% horizontal line. And that allowed us to turn probabilities into actual predictions, so either yes or no. Now let's take a step back. Where did we get these 4 values from? So we took 4 random values of the independent variable, and we just had a look at what would happen to them, how we would use the logistic regression function to ascertain what probability they have and what y hat values they have. So how about we take another step back and we forget about these 4 random values, and instead of taking 4 random values of the independent variable, how about we take 4 known values? In fact, let's take 4 values for the independent variable from our data set. So let's just pick out 4 values that we already know they exist in our data set, and we use them to create this logistic regression. And let's do the same thing with them. Let's see where they will end up if we apply the model to them. And as you can see here, the label of the vertical axis changed to y, because this is we already know that in red is the actual value of the dependent variable, because we know the result. Those the people on the bottom, so observations number 1 and number 3, they didn't take up the offer, the email offer, and the observations on the top, people number 2 and 4, they did take up the email offer. So let's see what happens to them if we apply our logistic regression model. So step number 1 would be to project these values onto the curve. Makes sense, right? So we just want to see where they'll end up on the curve. That's our blue dots over there. That's where they have been modeled by the curve. Now from here we can say what the probabilities are. You just have to project to the left, and you can see approximately that for observation number 1, it's about maybe 20%, 10, 15%, maybe let's say 15%. Observation number 2, it's about 40%. Observation number 3, I would say about 70%. Observation number 4, about 85%. But we're not interested in probabilities per se right now. What we want to get to is the actual y hat. We want to see what the predicted value will be. So we want to see if the model will tell us, are these people going to take up the offer or not? And why do we want to do this is because we already know the result, right? We already know what the result will be or was, and we just want to see, we want to kind of assess the model. We want to see how well it's working and if it's going to make any mistakes. So let's go ahead and proceed with our logic for getting the y hat. And what was our logic there? Well, the same thing that we discussed just a few minutes ago at the start of this tutorial. We're using this arbitrary horizontal line, 50%. So anything below this line is going to be projected onto the horizontal line, which is 0. So where we're saying that the offer is not going to be taken up. And anything above the 50% line will be projected onto the horizontal line, which is 1 or 100%, where we're saying that those people that end up on that line are definitely going to take up the offer. So let's go ahead and do that. There we go. In gray, we have our projections or our predicted values. So y hat is in gray. And it's very interesting to see both y and y hat on one chart. So that means what actually happened is in red and what we predicted was going to happen is in gray. And right away you can see that for observations number 1 and number 4, so for those people in observation number 1, number 4, we predicted correctly. So we said for person number 1, we predicted that he won't take up the offer, and he actually did not take up the offer because the red mark is also on the same horizontal line. Now for observation number 4, same thing. We predicted that that person will take up the offer, and they did take up the offer. That's good. But now let's have a look at observation number 2 and number 3. You can see that for observation number 2, the gray line's at the bottom, the gray mark is at the bottom, meaning that the model is predicting for this person based on their gender, based on their age. Well, in this case, just age, because we're doing a single variable logistic regression. So based on their age, this model is saying that this person is not going to take up the offer because the gray mark is at the bottom. However, we can see that the red mark is at the top, meaning that this person did take up the offer. And that means that the logistic regression made an error here. And same thing for person number 3. The gray mark is at the top, and that means that the model is predicting that the person will take up the offer, but the red mark is at the bottom, meaning that the person didn't actually take up the offer, and therefore the logistic regression made a mistake once again. And these mistakes, they actually have specific names. So the top mistake over there is a false positive, or a type 1 error. What does false positive mean? Well, it means that we predicted a positive outcome, but it was false. So we predicted an effect that did not occur. And the other mistake you see here has a different name. It's called a false negative. So we predicted that there won't be an effect, but the effect actually did occur. So our prediction was negative, meaning there won't be an effect, but it was a false negative. And it's called a type 2 type of error. And the way I personally remember them, it's important also to distinguish between the two. The way I personally remember them is I think of type 1 as less dangerous than type 2. So type 1 is less for me in my mind, although it's not necessarily the case, but that's the way I remember them, that type 1 is kind of like a warning. So that's why there's an orange exclamation mark, and it's a false positive. So basically, you said something's gonna happen, but it didn't happen. So you said maybe there'll be an earthquake, but there wasn't an earthquake. So that's not the end of the world. But false negative is a bit worse in my, once again, understanding, because if you say something's not gonna happen, but it actually does happen, then you can't even be prepared for it. And that's why type 2 is a false negative, and that's how I remember them personally. But once again, it could be absolutely, they can both be pretty serious errors, especially when you are dealing with like medical conclusions and stuff like that. So those are false positives and false negatives. We will be using them more when we talk about the confusion matrix in the next tutorial. And I look forward to seeing you next time. Until then, happy analyzing. Confusion matrix. Don't you just admire these terms sometimes that they come up with? Like, why would you call something the confusion matrix when it's designed to explain things? Anyway, let's get into the confusion matrix. So, last time we left off over here where we discussed false positives and false negatives, type 1 errors and type 2 errors. So, the false positive is when you predict that something will happen, but it actually doesn't happen, and that's a type 1 error. And a false negative is when you predict that something won't happen, but it does actually happen, and that's a type 2 error. So let's see what we can do with these. Let's start building a matrix, and we'll understand what it is exactly saying as we get along with it. So we've got the y hat at the top, so the predicted dependent variable, so whether or not we're saying that event will happen at the top, and on the left we've got the y, just the y, the actual dependent variable. So there it's telling us whether or not that event actually did happen. Now under each one of them, let's put the two different options that are available. You can either have a 0 or a 1. So 0 for y hat, 1 for y hat, 0 for y, and 1 for y. And in that space between them, there's 4 more squares there. That's where our confusion matrix will be. So we'll start with the furthest square. Right away here, that is the intersection of when y hat is 1, so we're predicting something will happen, or the person will take up the offer, or the event will occur, and at the same time it actually did happen. So let's say, for instance, we had 50 observations in there, or out of our observations, the ones that we said will happen and actually did happen, there's 50. Now let's look at the ones that didn't happen, and we also said that they won't happen. So basically we said they won't happen and they actually didn't happen. So let's say that in there we have 35. So 35 of the observations, let's say in total we have 100, and 50 of them actually did happen, and our prediction was that they will happen, and 35 of them, they didn't happen, but we also said that they won't happen based on our model. Now let's look at the other two squares. So can you guess from here which one is the false positives and which one's the false negatives? I'll give you a second to do that. You can pause the video if you want to try this on your own. So the false positives, or the type 1 error, are at the top on the right, because a type 1 error is when you're saying that something will happen but actually doesn't happen. And remember, the way I remember it is, it's not as bad as saying that something won't happen and it actually does happen. Although that might not necessarily be the case, but it's an easy way to remember it. So that's our type 1 error. It's up at the top over there on the right. Now on the left at the bottom, we've got the false negative, or the type 2 error, when we're saying that something won't happen but it actually does happen. And let's say we had 10 and 5 in them respectively. So this is your confusion matrix, and what it's telling you is it's giving you a quick overview of how well your model is performing. If you look at the diagonal, the light diagonal, it won't be colored probably in the report that you'll be studying, but if you look at the top left and the bottom right, if you just remember in that way, those are the good things. So in total, that's how much you predicted correctly. And the other diagonal, so the top right and the bottom left, those are the bad things. Those are the observations that you weren't able to predict. Those are your errors. So the more you have in the first diagonal, the better. The more you have in the second diagonal, the worse your model is performing. And let's have a look at two ratios that you can calculate. So the first rate is the accuracy rate, and you take the correct predicted divided by total. In our case, we predicted correctly 85, the total is 100. So if we divide 85 by 100, we get an 85% accuracy rate. And you can tell it right away just by looking at the confusion matrix, especially if you know the total number of the observations right away, so you don't have to do the calculation, add up all the values in the matrix. That way you can just divide by 100. But even by looking at the confusion matrix, you can quickly understand what the accuracy rate is, and also the error rate. So you take the total that you were wrong about, and you divide by the entire total. So in this case, it's 15 divided by 100, it's 15% error rate. That's all for today. We'll be using the confusion matrix in our next tutorial. Here I've got a confusion matrix, and this confusion matrix has 10,000 records in it, and it represents scenario number 1, which we'll be looking at. As you can see, this model has made 150 type 1 errors and 50 type 2 errors, but overall is predicted quite a lot correctly. Now let's calculate the accuracy rate in this scenario. The accuracy rate is the total correct divided by the overall total, and it's 9,800 divided by 10,000, which is 98%. Okay, great, but what we're going to do now is we're going to tell the model to stop making predictions whatsoever. We're just going to abandon the model completely, and we're going to say that from now on, our prediction is always 0. We're always going to predict that the event is not going to occur. So basically what will happen to the confusion matrix is these records will move from the right column to the left column, and our new confusion matrix will look like this: 9,850, 150, and then nothing in the predicted column where we predicted that something will occur. And of course that move is against all logic, right? Why would you abandon a model? But let's calculate the accuracy rate in this scenario. Scenario 2, accuracy rate has the same formula. In this case, accuracy rate is 9,850 divided by 10,000. So it's 98.5%. The accuracy rate went up by 0.5%. And as you can see, what we did is we just completely stopped using a model, but the accuracy rate went up. And that is why you should not base your judgment just on accuracy rate, because things like this can happen, and even though obviously you're not using a model anymore, which means that you're not applying any kind of logic into your decision-making process, your accuracy rate is going up. So it's misleading you into a wrong conclusion that you should stop using models. And this effect is called the accuracy paradox. And starting from the next tutorial, I will show you a much better way to assess your models using the cumulative accuracy profile. I look forward to seeing you then. Until next time, happy analyzing. In the previous tutorial, we talked about the accuracy paradox. Hopefully now you see why we need more robust methods to assess our models. And today we're talking about the cumulative accuracy profile, which is in fact one of those methods. Let's look at a scenario. Let's say you're a data scientist at a store which sells clothes, and your store has a total of 100,000 customers. I'm placing that number on the horizontal axis. And you know that from experience, whenever you send an offer, like an email to all your customers or to any random sample of your customers, approximately 10% of them respond and purchase the product. So I'm going to place 10,000, which is 10% of the total, on the vertical axis. And so what we're going to do is we've got an offer that we want to send, and we want to see how many customers are going to purchase our product if we send it off. So if we send it to 0 customers, obviously we'll get 0 responses, right? What do you think will happen if we send it to 20,000 customers? How many do you think will respond? Well, because this is a random sample and we know that about 10% respond, so we would say about 2,000 would respond. Fair enough, right? If we send to the offer to 40,000 of our customers, then about 4,000 will respond. 60,000, 6,000, 80,000, 8,000, 100,000, then 10,000 of our customers should respond. And this is a random selection process. So here we can draw a line which will actually represent this random selection. The slope of the line equals to that 10% that we know that respond on average to our offers if we just send them out like that. Now the question is, can we somehow improve this experience? Can we get more customers to respond to our offers when we send out our letter? So basically, can we somehow target our customers more appropriately so to get a better response rate? And how about, instead of sending out these offers randomly to say a random sample of 20,000 customers, how about we pick and choose the customers we send these offers to? And how do we pick and choose? Well, to start off with, let's build a model just like we did in the previous section. Basically a customer segmentation model, a geodemographic segmentation model, but which won't predict whether or not they will leave the company. It will actually predict whether or not they will purchase the product. It's a very similar process. Actually, in fact, it's the same thing, because purchased is also a binary variable, yes or no. And we can also run the same experiment. We can take a group of customers before we send out the offer and then look back and see who purchased, were they male or female, which country were they in, what age predominantly were they browsing on mobile, or were they browsing via computer? And all of these factors, we can take them into account, measure them, put them into a logistic regression, and get a model which will help us assess the likelihood of certain types of customers purchasing based on their characteristics, so their geodemographic status and other characteristics. And once we've built this model, how about we apply it to select the customers we will send the offer to? So what the model will tell us, just like in the example in the previous section where female customers of a bank whose favorite color is red, they're most likely to leave the bank. Here we'll have a similar result. It'll say perhaps male customers in this certain age group who browse on mobile are most likely to purchase a product. It will tell us something, or it'll actually rank our customers. It'll give them a probability of purchasing our product, and then we can use that probability to actually contact our customers. So of course, if we contact 0 customers, we'll get a 0 response rate, but if we contact 20,000, we'll probably get a much higher response rate than just 2,000, because we're picking out the customers that are at the highest risk of accepting this offer. We know from their previous behavior, or from the previous behavior of customers similar to them, that they have a 90% chance or an 80% chance of purchasing this product, and we will go for them first. We will put them at the top of our list of people who we contact. Then when we contact, let's say we contact not 20,000 but 40,000, our response rate will be higher than 4,000, which we get in the random scenario. If our model is really good, then by the time we're at around 60,000, so just over half of our total customer base, we're already getting to that 10,000 mark. So we know that 10,000 people will respond in total. There's no way we can get above that, because that's just the response rate. If we contact everybody, it'll be 10,000, but we're getting very close already. So even at 60,000, we're already at 9,500 respondents or purchases. We could actually stop here. We've already pretty much contacted everyone. But if we want to contact more, if we send it out to 80,000, we're getting even closer to 10,000 responses. And if we contact 100,000, we will still be back at our 10,000 responses. So now let's draw a line through these crosses. So what you see, this line here is called the cumulative accuracy profile of your model. And as you can imagine, the better your model, the larger will be the area under this line. So the area between the red and the blue lines, it will increase as your model gets better. And if your model is worse, then this red line will be closer to the blue line, so it'll be closer to random. The next step we want to do is convert these axes from absolute values to percentages. So they range from 0 to 100%. And this is how the cap curve is normally represented. Now let's say we ran another regression model, and this time we used less variables, less independent variables, or just because we had less access to independent variables, or we didn't see that there's a multicollinearity effect in a model, or something else that went wrong. And that model, because it'll be worse, this is what its cap curve will look like. And therefore, by plotting the cap curves, you'll be able to compare models to each other and understand how much gain, this is also sometimes called the gain chart, how much gain you get in each of these models compared to the random scenario, or how much gain you get, additional gain you get from switching from one model to the next, or from the green one to the red one, for instance. You're improving your hit ratio, and therefore you're improving your return on investment. So therefore the red model is better, and this is how we are going to be assessing models. So let's label them. The blue line is a random selection process. Like a monkey could do that. You just pick out random sample and you send the letter, or you just send it to everybody. You get your 100% of respondents. The green line is a poor model. So it's a model, it's better than random, but it's still not as good as the red one. The red one is a good model. As you can see here, at around the 50% mark, we're getting just over 80% responses. That's considered a good model. And there's one more line that you can think of here, and it's this line. This line is the ideal line, and this is what would happen if you had a crystal ball. If you could predict exactly who is going to purchase and contact those people, this is what it would look like. Why? Well, because if you look at that, the place where that spline occurs, you will see that it's exactly 10%. And 10%, as you remember, we know that only 10% of our customers ever purchase. So basically, you're saying that on the horizontal axis, I'm going to take 10%, and each and every single one of those customers I pick in that 10%, they are going to be those that purchase. That means I will go right straight to 100% with this last scenario. This actually took me a while to get my head around when I first heard about it, because I never understood why is there this spline at the top, why does it break like that? But that's exactly the reason, because you can imagine that you have a crystal ball and you contact in the first 10%, or however many in your specific business scenario customers ever purchase. You contact them right away, and then it's just flat from there, because it doesn't matter how many more you contact, they're not going to purchase. That's just the reality of things. And that is the curves that you can have on a cap curve. If you ever see a model that goes under the blue line, I didn't even draw one here, but if that happens, that's a very bad model. It's basically doing you a disservice if you see the curve under the blue line. And we'll talk about model deterioration further in the course when we're talking about maintaining a model. So that's it for the cap curve. For the introduction to cap curve, we'll be using the cap curve very actively in this section to assess our model. And in fact, we'll actually build two of them, and one for our model and one for our test data. So that will be very interesting to compare. One last thing I wanted to mention is a note that we have the CAP, which is a cumulative accuracy profile, and we have a ROC, which is a receiver operating characteristic. A lot of people get these things confused, and myself included, I used to get it confused. I even tried proving one time a colleague of mine who knew this stuff really well at the time, when I was just learning it, that he was wrong, but that was a funny experience. But they're not the same thing. So cumulative accuracy profile is the one we talked about. Receiver operating characteristic we won't be covering in this course. It'll be in my advanced course on statistics. It's very similar, it looks similar, and that's why a lot of people get it confused. And actually, I think the other reason is that the ROC curve is in Wikipedia. There's an article for the ROC curve, but there isn't one in English for the cumulative accuracy profile. So it's quite hard to find information on the CAP curve just by searching in Google. So maybe you'll be the first person to write a Wikipedia article on the CAP curve. Who knows? Maybe. Anyway, I look forward to seeing you in the next tutorial, and where we will be working with the CAP curve. And until then, happy analyzing. CAP analysis. We've talked about CAP a lot, and in fact we've talked about CAP that much that I'm no longer even saying cumulative accuracy profile, because I am assuming that you're entirely comfortable with this abbreviation and the whole term and what it means. So let's see how to analyze the CAP. As we've discussed, there are three lines that are important on the CAP curve. The blue line, which is the random line, when you select your samples at random. The red line, which is our model line, and different models will have different red lines, but basically it looks something like that. And the gray line, which is the perfect model, or when you have a crystal ball, when you can select all of the future churners or purchasers or whatever action takers, and you can select them right away on the dot without even selecting one single person that you don't want to select. And so these are the three main lines. And how do we analyze this cap curve? We already know how to build it, but what can we derive? What insights can we derive from here? Well, it's kind of intuitive that the closer your red line is to the gray line, the better your model. The closer it is to the blue line, the worse. So how can we quantify this effect? Well, there is a standard approach to calculate the accuracy ratio. And to calculate the accuracy ratio, you need to take the area under the perfect model or the perfect line, which is colored in gray here, and it's called the AP. And then you need to take the area under the red line, which is colored in red here, which is AR. And then you need to divide one by the other. So you need to divide AR by AP. And then this ratio that you get is obviously between 0 and 1. And the closer this ratio is to 1, the better. The further it is away from 1, closer to 0, the worse. However, it can be quite complicated to calculate this area under the curve. Statistical tools can do it for you, but how can you assess the cap curve by just looking at it, so visually? It's not that easy to get this quantifiable metric just by looking at the curve. So there's a second approach, and that's what we're going to discuss now. Let's get rid of the areas, and instead of looking at the area, what you can do is look at the 50% line on the horizontal axis and look where it crosses your model, and then look at where that line, the horizontal line from there, crosses the vertical axis. So basically, how many churners will you pick up, or action takers, or how many positive outcomes are you going to identify if you take 50% of your population? And in this case, we can see it's around 90% or something like that. And just by looking at that, there's a rule of thumb how you can assess your model based on that X number. And here it is. Are you ready? Here we go. So if X is less than 60%, the model is rubbish. Basically, it's not useful at all. You can create a better one. Probably you can create a better one, and you need to try again. If your model, your X is between 60% and 70%, then the model is considered to be poor or average. And by the way, this is my rule of thumb. Other people might have a different rule of thumb, but this is what I go by. If it's between 60% and 70%, it's a poor model, to be honest. Like you can do better than that. If X is between 70% and 80%, that's a good model. That's already where you should be aiming for. Anything above 70%, that can deliver good quality insights to the business and actually deliver value. Anything between 80% and 90%, like we see here, is very good. It's extremely good. If you can get a model over 80%, that is an amazing result. And anything above 90% up to 100, that is just too good. It is too good to believe, and there's one option that you should be very careful here with, is overfitting. If your model is showing you results like 90%, or say if a model is showing you 100%, then the obvious answer there is that one of your independent variables is actually a post factum variable, meaning that it shouldn't be in the data because it's looking into the future. The person who supplied you that variable forgot to take it out, or forgot to explain to you that their credit score actually is turned into 0 after they leave the bank, and therefore everybody with a 0 credit score obviously has left the bank, and therefore your model is picking them up like it's super easy. So if you have 100%, that's definitely something wrong with your variables. Even if you have 90 to 100%, you have to check that there could be some forward-looking variables. The other thing is overfitting. You could be overfitting your model, and what that means is that your model has been so well fit to that specific data set that you supplied it, that when you that it's just heavily relying on the anomalies in that data set. And when you feed it a new data set, like in a month time or something like not training data, not the data that you trained your model, and we'll talk about this a lot more actually in the coming tutorials. But so if you feed this model some data that you want to actually predict on, then it will crash. Well, it won't crash. It won't perform as well. It will perform, at the 60% mark or something. So that means your model is overfitted, and be very careful about that. We'll talk about overfitting more. In fact, in the coming tutorials, we will learn how to avoid that problem. And finally, if you can get an X or this parameter to be between 90% and 100% and you're not using forward-looking parameters, or you're not overfitting, then give me a call, because I might have a job for you. People like that are rare, and I have a lot of headhunters looking for people who can do modeling like that. So definitely keep that in mind. And I look forward to seeing you then. Until next time, happy analyzing.